So we're going to be talking about applications for radian measurements. Remember we talked about degree minute seconds and radians now as our two different types of units for angles. And now we're going to be applying the idea of radians to show you where it might be useful. The first thing is, if I had a circle, radian measurements for angles will help us to find arc lengths and angles for sectors or small portions or wedges out of a circle, kind of like pie pieces out of a pie. Okay, so if I were to have a circle with a certain radius, we'll call it r, and some angle here, we'll call this angle theta, then the corresponding arc length, which is the length around the curve of the circle, has a length of s. We call s, I don't know, for whatever reason we use the letter s for the arc length, okay? So r, theta, and s. And so I want you to think about this for just a minute. There's a proportion that's going to be very important. In some sense, it's kind of like when we had similar triangles and we said that ratios of corresponding sides are always equal. Well, with circles, we can think of it this way. There's a proportion. If you had the proportion, like the angle that opens the whole circle, that's 2 pi, right? And you have a circumference around the whole circle, which is 2 pi r. Well, if you take just a portion of the angle, let's say you took half of the 2 pi or 360 and just opened it halfway, that'd be a 180 or a pi angle, you would swipe out half of the circumference. If you wanted a quarter of the circle, you'd swipe out a quarter of the circumference. And so the proportion, the amount of this angle is going to be equal proportionally to the amount of the circumference that's swiped out. And so the ratio then between the angle of this sector, theta, and the total angle of the circle, which is 2 pi radians, that ratio between the angle of the sector and the angle of the circle is equal to the ratio between the arc length of the sector and the arc length of the entire circle. So the arc length of the sector to the arc length of the entire circle. Well, the arc length of the entire circle is just the circumference of the circle. Okay? And so if I wanted to solve this, it's kind of messy. It's got a lot of variables and some other stuff in it, but I'm going to solve this by first replacing the circumference by a formula that I know it's equal to, namely 2 pi r. I know that the circumference is 2 pi times the radius. We talked about that in a previous video. And so if I were to replace the c with 2 pi r, you'll see we're starting to get some similarities here on each side of the equation. To get rid of the fraction, I might multiply by the least common denominator, which is 2 pi r. So I'm going to multiply both sides of this equation by 2 pi r. And what's nice about that is on the right side, everything in the denominator cancels out. The 2, the pi, and the r, they all drop out. On the left side, the 2 drops out and the pi drops out, but the r stays. And so what we end up with is r times theta, is equal to s. Well, that gives us an equation that just relates those 3 pieces of information to each other. In fact, you'll see this in your book, more commonly written as s equals r theta. Again, theta needs to be in radian measure in order for this to work out. So where theta is in radians, okay? And the reason it has to be in radians is because when I defined this initial angle, I used 2 pi, which is a radian measure for the the full angle around the circle, in the formula. Okay, so we have to go radian to radian here. Okay, so this is a nice formula for the arc length of a sector. Okay, if I didn't say this already, a sector is just a pie-shaped portion of a circle. I think I mentioned that. Just so it's clear, it has to have a vertex at the center, and then it's just kind of a pie-shaped portion, so it 2 radii coming out, and it swipes out a portion of the arc length. Okay. Okay. So let's see. Oh, then another formula. So that's a formula for the arc length, S. There's another formula for the area. Areas are proportional in the same way. If you swiped out half the circle, half the angle, you would get half the area, the upper half versus the lower half. Or a quarter. If you took a quarter of the angle, you get a quarter of the area. So areas are also proportional. Your book, and so my math lab, will use a sort of a script A. I'm not sure I'm even writing that very well. It's like a cursive A, or not really cursive though. It's like a weird italicized font. Let's see if I can draw it very well. There, it looks something like that. I don't know. It's a script A of some sort, or an italic A. And so the ratio, just like before, this ratio of theta to 2 pi must be equal to the ratio, so that's the ratio of the sector to the whole circle, must be equal to the ratio of the area of the sector to the whole circle. So that would be the script A over the overall area of a circle. Well, we also know, in addition to the circumference formula, we know that the area is pi r squared. Okay, we talked about that in another video. And so if I replace A with pi r squared, I get theta over 2 pi equals area of the sector over pi r squared. Again, I want to multiply both sides by the LCD, but actually I'm going to leave the 2 off. I'm going to pretend the 2 is not there in the denominator. This just becomes a little bit nicer formula if I leave the 2. Really, ultimately, I want to solve for this area. Okay, so really that's what I'm doing. Solving for A, I got to multiply both sides by pi r squared. So I'll do that. Multiply by pi r squared. Multiply here by pi r squared. And the denominator completely cancels on the right. And on the left, the pi cancels, and that's it. And so I'm left with, you could think of it as r squared theta over 2 is equal to that area of the sector. However, we're generally going to write this, instead of dividing by 2, we're going to write it as a coefficient of 1/2. It's the same thing. And so the area then is equal to 1/2 r squared theta. All right, so this is the common form, and again, you must have the theta in radian measure for that to work. So where theta is in radians. Okay, so there's 2 formulas to keep in mind as we work through the rest of the examples in this section. And so moving forward, we're just going to be choosing some examples of applications where we're going to be utilizing these 2 formulas to solve different types of problems.